In this video, Chapter 5, we'll be covering the 9 techniques of integration. And so we'll be starting off with the basic integrals. So the first thing we'll be covering is differential operator is a linear operator. And this can be seen by L of a times f of x plus b times g of x is equal to a times L of f of x plus b times L of g of x. And so then we can compare this to a differential operator. D over dx times 2x cubed minus 4 sine x is equal to 2 times d over dx x cubed minus 4d over dx times sine x. They're pretty much the same. And if we were to take the derivative of that, we would get 6x squared minus 4 cosine x. Moving on, the inverse of differential operator is called integral operator and is also a linear operator. The symbol for integral which operates on a function f of x is integral f of x dx is equal to antiderivative of f of x. However, things to be aware of is that the integrand f of x lies between the integral symbol and dx, while the antiderivative f of x is noted by a capital letter. And so in this slide, here are some examples of functions and their derivatives and antiderivatives. And so here in the first row, we would have the derivative of f of x, or on the left. In the middle, we have the function, and on the right, we have the antiderivative. And so as you can see, the function x to the power of n, if we take the derivative of that, we get nx to the n minus 1, and if we were to take the antiderivative of f of x, we get x to the power of n plus 1 divided by, whole thing, n plus 1 plus c. And so now let's look at some trig functions. Cosine a times x. We take the derivative of that, we would get negative a times sine ax. And then if we were to take the antiderivative of cosine ax, we would get 1 over a times sine ax plus c, again c being a constant that we have to consider. But if we were to take the derivative of the antiderivative, we would just come back to cosine a times x. And so now let's look at the trig function sine a times x. With like the antiderivative of that, we get negative 1 over a times cosine a times x plus c. And so now let's go back to the original function. Well, in order to do that, we just take the derivative of the antiderivative. And then if we look at our derivative of sine ax, we get a times cosine a times x. And now let's go back a row and let's look at the antiderivative of cosine. 1 over a times sine ax plus c. So if we take the derivative of that, we get cosine ax, right? Much like how if we take the derivative of the sine ax in the function, not the antiderivative, we get a times cosine ax. They match up. They go alongside each other. Just going back and forth. You have to be aware of the negative symbols. And so now in the next row, we'll be looking at the function, the exponential function, e to the a times x. We take the derivative of that, we get a times e to the a times x. And make note that nothing happens to the exponent ax. And now let's take the antiderivative of e to the a times x. We just get 1 over a times e to the a times x. And again, nothing happens to the a times x. And so now let's try applying some of this into integration. We can use integration to find the area of functions between certain intervals of our choosing. Let's try out with the function y of x is equal to cosine of 2 times x. We take the integral of both sides, we would get big Y of x is equal to integral from 0 to pi cosine of 2x dx. And let's make note that the antiderivative of cosine ax is equal to 1 over a times sine of a times x. And then after taking the antiderivative of that, we would end up getting big Y of x is equal to 1/2 sine of 2x. Of course, we cannot forget from 0 to pi, which is the area that we're choosing. And so now, let's remember that the derivative of sine ax is equal to a times cosine ax. And so if I were to take the derivative of 1/2 sine 2x, I would come back to cosine 2x, the original function. Which of course doesn't really matter much at this point, but it's good to make sure that you did your antiderivative correctly. If you're able to take the derivative of your antiderivative and come back to the same function, then you know that you did correctly. and then we plug in 0 and pi. We do pi first and then 0, so we get 1/2 sine 2 pi minus 1/2 sine 2 times 0. And then we would ultimately get 0. But why is that? What, we have 0 area from 0 to pi? Should area really be 0? Well, let's recall that the graph of cosine x looks like, well, it looks like this. And so the graph of cosine 2x will look like this. And as you can see, from 0 to pi, the graph becomes negative at certain intervals. And the graph of cosine x at pi over 2 to pi, it would be negative. The area over there would be negative, but you can't have negative area when searching for area. And so what do we do? Well, since we're looking for area, we should not account for area under the x-axis as negative, since, again, area cannot be negative. And so now let's bring the graph with us this time. Now, the function, again, y of x is equal to cosine of 2 times x. Let's make note of where we get positive area and where we get negative area. From the integral 0 to pi with the function cosine of 2x dx. And so now looking at the graph, where's our first positive area? Well, our positive area, our first one is from 0 to pi over 4. And so that would be our first integral, because we want the area from 0 to pi over 4, which would give us 1/2. And now let's look, now we have to get the negative area. We get the negative area from pi over 4 to 3 pi over 4. And so we would take it, that would be our points for our integral, pi over 4 to 3 pi over 4. And then afterwards, we continue to our positive area, which is from 3 pi over 4 to pi. And so what we did is that we took in 3 separate integrals, and now we would have to take the absolute value of the negative area, because again, area cannot be negative, and we're looking for area between 0 to pi. And so again, absolute value of the negative area, we add it together with the first positive area and the last positive area to get our total area from 0 to pi. And so now moving on, we would go into use substitution. And so in use substitution, we have to consider 2 things. The first one being is that the use sub technique can either change the integral to a basic integral, or the second one being into an integral that can be solved by another technique. And in my opinion, the use sub is all about the ability to see a function if the derivative of the function is given. And to do this, to solve an integral by u sub, we would take part of the integral as u and the rest as du. And then the second step being that we transform the integral into a function of u and integrate in terms of du. Now let's apply this. We have the integral tan x times secant squared x dx. And the first step being we let u equal to tan x. And then we take the derivative of that, we get du is equal to secant squared x dx. And then at that point, we would substitute it. We would substitute u and du in, for we announced that we declared that u is equal to tan x, and du, the derivative of u, is equal to secant squared x dx. And then at that point, we integrate in terms of du. And then we plug u back in, and we get tan squared x over 2. And now after learning how to use u sub and applying it, we could also use u sub to simplify integrals, which we would use trig identity afterwards. And this can be seen in integrals in the form of integral cosine to the power of m and x sine to the power of n x dx, and integral tan to the power of mx times secant to the power of n x dx. So let's look at the integral in the form integral cosine to the power of mx times sine to the power of nx dx. And so if m, which is respectively belonging to cosine, is odd, we would take out one, we would subtract 1 and be able to bring out cosine from it, which looks like integral cosine power to m minus 1 x sine to the power of nx cosine x dx. Again, we got that cosine x from subtracting from cosine to the power of mx. And so then at that point we have trig identities, we were able to substitute, and then afterwards we would use substitution. And same thing for case 2, if n respectively belonging to sine is odd, we would subtract 1 from sine, the exponent. Sine, it would look like sine to n minus 1. We would just do that and be able to bring out a sine x. And then at that point we would use trig identities, substitute in, and then we would let u equal to cosine x, and du, the derivative, equal to negative sine x dx. And at that point it's just taking the integral of trig functions. And then lastly, case 3, if m and n are even, we would just use trig identities to simplify and then integrate, which is pretty much what we've been doing for case 1, case 2. We're just trying to get them to be even so that we would be able to manipulate it with the trig identities. Now let's look at the other integral, the integral in the form of integral tan to the power of mx times secant to the power of nx dx. And again, these also have 3 cases, but they're quite similar to each other. Now let's look at the first case. If m respectively belonging to tan, is odd, we would take out tan and secant, which would look like tan to the power of m minus 1 x times secant to the power of n minus 1 x times tan x secant x dx. And following trig identities, we would let u equals secant x and du equals secant x tan x. And similar for case 2, if n is even, n respectively belong to secant, we would have to take out 2 secants. And so then, in order to do that, we would just subtract n by 2. And so it would look like integral tan to the power of m x secant to the power of n minus 2x times secant squared x dx. And then at that point, after trig identities, we would let u equal tan x and du equals secant squared x dx. And then for case 3, if m is even and n is odd, we would just use trig identities to simplify and then integrate.
So yeah, sometimes when you're trying to find the integral of the product of 2 trigonometric functions, taking a u substitution won't really simplify the integral at all. And in this so-called case 3, you would need to use a trigonometric identity to simplify the integral. As you can see, there are a lot of trigonometric identities here. Not even all of them are here. Any one of these could help you simplify an integral. So, like, you could have an integral be simpler if you expressed it as the sine of the sum of 2 angles, or the sine of a difference of 2 angles. If it's a sum, you can take it as sine of the first times cosine of the second plus cosine of the first times sine of the second, or a difference, sine of the first cosine of the second minus cosine of the first sine of the second. Or maybe the cosine of a sum of angles, or cosine of a difference of angles. And that'll be the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second if it's a sum of angles, or cosine A, cosine B plus sine A, sine B if it's the difference of 2 angles. Sometimes it'll be exactly double of an angle, in which case it'll be sine of A plus A, or 2 times sine A cosine A. Or maybe sometimes it'll be double cosine angle, cosine A plus A. And then there's the tangent of double angle, and that would be 2 times the tangent of the first angle divided by 1 minus tan squared of that angle. So yeah, there's also ways of simplifying squared angles, like sine squared of A. That can be expressed as 1/2 of 1 minus cosine of double A. Or you could express cosine squared of A as 1/2 of 1 plus cosine of double A. And tan squared of A is equal to sine squared of A of cosine squared of A. Easy. Then there's ways of writing it that are 1 sine plus another sine. And you can write that as 2 times the sine of the first angle plus the second angle divided by 2 times cosine of the difference of the first angle minus the second angle divided by 2. Or maybe it's sine of an angle minus a sine of another angle. And that would be 2 times cosine of the sum of the angles divided by 2 times sine of the difference of the angles divided by 2. Or maybe it's the cosine of one angle plus the cosine of another angle. That's cosine times 2 of the sum of the angles divided by 2 times cosine of the difference of the angles divided by 2. Or maybe the one cosine minus another cosine, and that'll be negative 2 times sine of the sum of the angles divided by 2 times the sine of the difference of the angles divided by 2. And then there are ways of writing it as the product of two signs, like sine of A times sine of B. And you can express that as the cosine of the difference of the angles minus the cosine of the sum of the angles, and divide that by 2. And maybe it's the cosine of an angle times the cosine of another angle, and that would be the cosine of the difference of angles plus the cosine of the sum of the angles divided by 2. And then if you want to get freaky, you could take the sine of one angle times the cosine of another angle. That would be equal to the sine of the sum plus the sine of the difference divided by 2. And then you could even take cosine of one angle times the sine of another angle. It's the sine of the sum of the angles minus the sine of the difference of the angles divided by 2. So let's take an example, actually. Let's take an example in the form tan to the mx secant to the nx. In the case 3 where m is even and n is odd. Let's find the integral of tan squared x secant x. And we can express that as the integral of secant squared x minus 1 times secant x. And that could be equal to the integral of secant cubed x minus the integral of secant x. And let's leave secant cubed x alone for now. Secant x integral, multiply it by 1, or secant x plus tan x divided by secant x plus tan x. And now you can express it as the whole thing as secant cubed x minus secant squared x plus secant x tan x over secant x plus tan x dx. And now you can use u substitution. Let u equal secant x plus tan x. You can let du equal the derivatives, secant x tan x plus secant squared x. Now you can express the whole thing. The integral of tan squared x secant x equals the integral of secant cube x dx minus the integral of du over u. Got easy. So it's secant cube x dx minus ln of u plus c. That's the integration. And that's equal to the integral of secant cube x dx minus ln of secant x plus tan x, and then plus c, the constant. Now let's take secant cube x integral. And now you can express the secant cubed x dx as the integral of secant x times times secant squared x dx. The whole thing equals the integral of secant x secant squared x dx. Now minus ln of the absolute value of secant x plus tan x plus constant c. And if you use integration by parts now, you can let u equal to the first secant x, and dv equal to the secant squared x dx. And you can let du equal secant x tan x, and v equal to tan x. And follow this formula. The integral of u dv equals uv minus the integral of v du. In the form of the actual problem, I'm just going to leave the ln of absolute value of secant x plus tan x plus c here on both sides, so that I don't confuse myself. The whole thing, secant cubed x dx minus ln of absolute value of secant x plus tan x plus constant c equals secant x tan x minus the integral of tan x secant x tan x dx minus ln of absolute value of secant x plus tan x plus constant c. That second integral can also be expressed as tan squared x secant x. How familiar. The original problem, tan tan squared x secant x dx equals secant x tan x minus the integral of tan squared x secant x dx minus ln of secant x plus tan x, absolute value, plus constant c. You move the integral to the left now, and you have 2 times the original integral, 2 integral tan squared x secant x dx equaling secant x tan x minus ln absolute value of secant x plus tan x plus constant c. Divide both by 2, and you get the original integral again, integral of tan squared x secant x dx equals 1/2 of secant x tan x minus 1/2 of ln of secant x plus tan x absolute value. Technically it would be half constant c, but I'll just call it c. So here's your answer. I showed you how to use trigonometric identities to help solve the problem. In this problem, we use the Pythagorean identity, where tan squared x plus 1 equals secant squared x. I'm sorry I kind of left this one off. I guess I assumed we all knew the Pythagorean identities, the cofunction identities, the negative angle identities, the easy ones. But with this Pythagorean identity, I was able to solve it. And integration by parts, and use substitution, and the better part of my life.
So now let's look at integration by parts. And so when is it needed? Well, it's needed when dealing with functions that are neither basic or composite. And in order to get that, we have to follow a certain rule. And in order to get the integration by parts rule, we will get that from the product rule. But what is the product rule? Well, the product rule in the derivative sense is the derivative of the whole thing, f of x times g of x, is equal to the derivative of f of x times g of x plus f of x times the derivative of g of x. And if we clean that up and make it look much simpler, if we let f of x equal to u and g of x equal to v, we would get the derivative of u times v is equal to v times the derivative of u plus u times the derivative of v. And if we want our integration by parts rule, all we have to do is just move v times the derivative of u over to the left. And now all we have to do to get our integration by parts rule is just take the integration from the product rule. And so then we get the integral u times dv is equal to uv minus integral v du. And so now that we have the integration by parts rule, let's apply it. Let's figure out the steps to actually integrate. And so now here we have an example integral of, well, in this case, big F of x, gx, dx. I did that for simpler purposes in order to see well. And so now we let u equal to f of x, and then we take a derivative du is equal to smaller f of x. And then we would get the dv is equal to g of x dx, because that's what's left. We let u equal to f of x, and we have what's remaining is g of x dx. So now we have to take the antiderivative of gx dx. We would get big G of x plus c. Remember that constant. And so now we just plug in. We plug into the integration by parts rule. And so after plugging in, we get f of x times g of x plus c times f of x minus integral g of x times smaller f of x dx minus integral c f of x dx. And notice that if we take the integral of c of f of x dx, the c's will just cancel out. And so what we have left is f of x times g of x minus integral g of x times smaller f of x dx. But exactly how do we know what to pick for u, what to let u equal to? Well, one thing I've learned recently is to think LIATE. LIATE is L-I-A-T-E, it's an acronym. And so L would stand for logarithmic functions like ln x. I would stand for inverse trig functions like arcsine and arccosine. A would be algebraic or polynomial function, ax to the power of n. And lastly, it would be trig functions or exponential functions. And trig functions and exponential functions are equal. They are on par with each other in choosing what u should be. And so according to this ranking, you would know what to let u equal to. And now that we know this, let's actually apply it. And so again, bringing up the integration rule, let's try integral x sine x dx. And so first things first, what do we have? We have a algebraic function and we have a trig function. And which one comes first, the algebraic function or a trig function? Well, the algebraic function comes first. And so we would let u equal to x and take the derivative of that, we get du equals to dx. And we would be left with is sine x dx, which would be equal to dv, and then we take the antiderivative of that. Antiderivative of sine x dx is negative cosine x plus c. And so now all we have to do is just plug in according to integration by parts rule, which is uv minus integral v times du.
Trigonometric substitution aims to simplify complex radical functions in the denominator into functions that can be more easily solved. In order to use this technique, we must understand two important Pythagorean theorem identities. The first one being 1 minus sine squared equals cosine squared x. The second, 1 plus tangent squared x equals secant squared x. Three other useful formulas are that if you have a radical with the form a minus x squared, you should substitute x with a sine theta. If you have the radical form x squared minus a, you should substitute x with a secant theta. If you have a radical in the form x squared plus a, you should substitute x with a tangent theta. Let's take a look at an example. Suppose we have to take the integral of 1 over radical 4 minus 4x squared. Now this radical is similar to radical a minus x squared, so we'll let x equal sine theta and dx will equal cosine theta d theta. When we substitute these values in, we'll get cosine theta d theta over the radical of 4 minus 4 sine squared theta. We can factor out the 4 in the denominator, and we'll be left with the 2 on the outside. Plus, we know that 1 minus sine squared theta equals cosine squared theta. So we can replace that, and the radical of cosine squared theta is just cosine theta. Thus, our integral simplifies to cosine theta d theta over 2 cosine theta. If we simplify that even further, we'll get integral of d theta over 2. The integral of that will just be 1/2 theta plus c. We can't leave this answer in terms of theta, however, because our original terms were in terms of x. So to convert this back, we'll have to look at our substitution value, x equals sine theta. We can easily convert this to theta equals inverse sine x. So let's substitute that back in. Our answer is now 1/2 inverse sine x plus c. Partial fraction decomposition is the process of taking a rational expression and decomposing it into simpler expressions to solve. We do this because it's easier to solve multiple components of an integrand rather than one complex integrand on its own. Let's do a quick review of partial fractions. We'll start with the rational expression in the form f of x equals p of x over q of x, where both p of x and q of x are polynomials and the degree of p of x is smaller than the degree of q of x. This is important to remember because partial fractions can only be done if the degree of the numerator is less than the degree of the denominator. So once we've determined that partial fractions can be done, we factor the denominator as completely as possible. Then, for each factor in the denominator, we can use the following table to determine which terms we pick up in the partial fraction decomposition. Notice that the first and third cases are pretty much really special cases of the second and fourth cases respectively. There are several methods for determining the coefficients for each term, and we will go over them in the following example. So let's evaluate the following integral, 3x plus 11 over x squared minus x minus 6. The first step is to factor the denominator as much as possible and get the form of the partial fraction decomposition. So we'll get a over x minus 3 plus b over x plus 2. The next step is to make both sides equal. We can do this by cross multiplication. We'll let a times x plus 2 plus b times x minus 3 over x minus 3 times x plus 2. Our next step is to solve for a and b. We can do this by letting both numerators equal to each other. So we'll get 3x plus 11 equals a times x plus 2 plus b times x minus 3. To solve this, we'll let 3x equal ax plus bx, and 11 equals 2a minus 3b. When we solve these two equations, we'll get b equals -1 and a equals 4. We'll substitute these two values back into a partial fraction decomposition. Thus, the integral of 3x plus 11 over x squared minus x minus 6 is the same thing as the integral of 4 over x minus 3 minus 1 over x plus 2. Completing the square is a procedure for rewriting an algebraic expression of the form ax squared plus bx plus c in the form a something squared plus constant. The concept itself is not difficult. You just need to learn how to find what that something is. We begin with simple examples where a equals 1. Let's try x squared plus 8x plus 7. Now the x squared and 8x terms both involve x, so they can't be part of the constant term. Hence, they belong with the something squared term. Now x squared plus 8x is not a perfect square, but x squared plus 8x plus 16 is the expanded form of the perfect square x plus 4 squared. So we'll add 16 to the expression in parentheses and compensate for this change by subtracting it outside the parentheses. Then we'll regroup, and basically we're done. In general, you begin by grouping x squared plus bx terms inside parentheses. What gets added to x squared plus bx? Well, b over 2 squared. But rather than trying to remember a formula, remember the idea. Take half of the x coefficient and square it. Add and subtract that quantity. Group the added part with the x squared and x parts, then rewrite, and you're done. Along with completing the square, there is a bit of trig substitution that goes along with solving integrals using this method. The chart below summarizes what to substitute in any given condition. Let's take a look at an example where we use completing the square to solve an integral. Let's take the integral of 1 over x squared plus 5x plus 7. Now remember the trick. Take half of the x coefficient and square it. Then we'll add and subtract that quantity. We'll complete the square on the denominator to get 1 over x plus 5 over 2 squared plus 3 over 4. Let's apply u substitution. We'll get u equal x plus 5 over 2 and du will equal to dx. Now our integral will be 1 over u squared plus 3 over 4. Since the constant term on the bottom is positive, we'll let a equal root 3 over 2 for now. If we take the integral, we'll get 1 over arctan u over a plus c, which equals to 2 over root 3 arctan 2u divided by root 3 plus c. Finally, when we replace u, we'll get 2 over root 3 arctan 2x plus 5 over root 3 plus c. This integral could be easily solved if there was no radical. We have devised some rules to manipulate this integral for us to solve it more easily. First, find the common multiply for the roots in the integrand. Second, let x equal u raised to the power of n, where n is the common multiply. Third, substitute and simplify, then integrate. Let's look at this example. The integral of 1 over x raised to the power of 1/4 plus x raised to the power of 1/3. In order to solve this integral, we need to find a common multiply between these two fractions. In this case, the common multiply would be 12. We'll let x equal u raised to the power of 12, then dx will be 12u raised to the power of 11 du. When we substitute this in, we'll get the integral of 12u raised to the power of 11 over u cubed plus u4 du. We'll factor out the 12 and factor out the u cubed in the bottom. The u cubed on the bottom and the u cubed on the top will cancel out, and we'll get 12 integral u raised to the power of 8 over 1 plus u. If we add 1 and subtract 1 on the top, we can split this integral into two parts. We'll get 12 multiplied by the integral of u raised to the power of 8 minus 1 over 1 plus u du plus the integral of 1 over 1 plus u du. When you take long division of the first integral, you'll end up with u raised to 7 minus u raised to 6 plus u raised to 5 minus u raised to 4 plus u raised to 3 minus u raised to 2 plus u minus 1 du, an integral of 1 over 1 plus u du. Now this integral is fairly easy to solve.
And lastly, we have sine and cosine elimination. And when is it needed? Well, it's needed when the integral is a rational expression containing sine x and cosine x. And how do you deal with them? You deal with them using half and double angle identities or using trig identities. And so in order to apply the sine and cosine elimination, I have to apply the half and double angle identities first. And so here I have a half angle triangle. Make note that the angle is x over 2. I can use this to find dx. And by figuring out what tan is, tan of that angle is. And so I would let tan x over 2 equal to u. And since we're finding dx, so I have to bring tan and 2 over. And so there'll be x over 2 equals arctan u. Bring the 2 over, it'll be x equals 2 times arctan u. And then you take the derivative of that, and we get dx is equal to 2 du over 1 plus u squared. And then we would want to find what sine x is, because remember, this is sine and cosine elimination. When we have sine x, we have to figure out how to eliminate that. And so let's make note of our double angle identity, sine 2x. Sine 2x should be equal to 2 times sine x times cosine x. And of course, sine x is equal to sine 2x over 2. And make note, let's just ignore the over 2 for a second. What is sine 2x equal to? According to the double angle formula, it's 2 sine x cosine x. But of course, we can't forget about the over 2, but we can still convert it. So that would be equal to 2 times sine of x over 2 times cosine of x over 2. And according to our half angle triangle, what is sine x over 2? Remember, sine is opposite over hypotenuse, and so that'd be u over square root of 1 plus u squared. And then now let's look at cosine x over 2. Cosine is adjacent over hypotenuse, 1 over root 1 plus u squared. And then we multiply that together, simplify, we get 2u over 1 plus u squared is equal to sine x. And so now we have to deal with cosine x, because remember we're also eliminating cosine. Cosine x should be equal to cosine squared of x over 2 minus sine squared of x over 2. And we get that because of the double angle identity, cosine 2x, which is equal to cosine squared x minus sine squared x. But take note that cosine x doesn't have a 2, and so then we would have to divide the x by 2. And then we look at cosine squared x over 2, that's cosine, we split that up, and we know what cosine x over 2 is, we just multiply, we would square that, and we get 1 over 1 plus u squared. And the same goes for sine squared x over 2. We would get u squared over 1 plus u squared. Subtract that, and we get 1 minus u squared over 1 plus u squared is equal to cosine of x. And so now let's actually apply it to a real problem. And so let's make note. Dx is equal to 2 du over 1 plus u squared. Sine of x is equal to 2u over 1 plus u squared. And cosine x is equal to 1 minus u squared over 1 plus u squared. Here our problem is integral dx over sine x plus cosine x. All we have to do is just plug in, it's all right there. Plug in and then simplify. And then we would get 2 du over 2u plus 1 minus u squared. And now let's rearrange the negatives, and then we could set it up as 2 minus parenthesis u minus 1 squared on the bottom. And so continuing from that, we could let z equal to u minus 1, and the derivative of that would be just du. And so then we substitute that in, and we get 2 dz over 2 minus z squared. And we take that a step further, and we could say that we could let z equal to square root of 2 times sine theta. Take the derivative of that, we get square root of 2 cosine theta d theta is equal to dz. And so our question would be, why did we include the root 2? Well, make note that on the bottom it's 2 minus z squared. In order to make this trig substitution correctly, because later on we're going to do trig identities, we have to incorporate that 2 somehow. And so then we plug it in, we factor out the 2, and then we'll be left with a simple trig identity. 1 minus sine squared theta is equal to cosine squared theta. And so after that, we could simplify, and we would be left with is the integral root 2 secant theta d theta. And then we take the integral of that, and we're all done.